All right. So, good afternoon. I'm Paul, and I'm in the AFNI group as well, and I'm going to talk about some things that relate a little bit to what Bob talks about, but a little bit more about visualization. So I think Bob went over a lot of the quantitative side and kind of what we look at in when this mouse is trouble when we're doing fMRI, and so there's a lot of tools in AFNI for doing statistics and things like that. We'll also take a look at why it's really important to look at your data and some different ways to do that, and some of the challenges when we have multiple different types of data to look at simultaneously. Bob talked a lot about fMRI, which is kind of gray matter centric and functional processing centric, and I'm going to talk more about structural white matter structures throughout the brain. And really, if you do have any questions, or if I don't explain something, please do just ask a question while something is showing on the slide screen. So, um, okay, so what Bob had just got to by the end of his talk was showing in AFNI this slice by slice view. So this is part of an axial slice, and we see our basic unit that we're visualizing is a voxel, these little squares that represent the three-dimensional voxel in space. And so when I talk about kind of AFNI, or when Bob talks about it, this is really what we're looking at in displaying this slice by slice in the brain, like a photograph through your head. And Bob also showed the time series, and so we can either look at a whole time series or kind of watch movies of these things through the brain, or a statistic that represents something important from the time series that we can calculate. But the brain isn't organized slice by slice. We have sulci and gyri and weird shapes that stretch and kind of go through any one given plane that we would look at. So it's nice to have a different kind of way to view the data in 3D, so embedded surfaces or linear structures in 3D. And that's really what I'll talk about here, which is SUMA, which stands for surface mapping. And so this is part of AFNI. It was done as kind of a separate subset, but now they're really merged. And this gives a bit of a sense here of how we can see the same data kind of projected onto the surface. And here it is just slice by slice. So same things, but different representations. We'll see why one's useful. And that's all the way to the end. Okay. So a lot of this, you've met Bob, who is the young Jedi Knight on the left. The person on the right is Ziad Saad, who is actually the person who programmed much of SUMA. And increasingly, this slide was made a long time ago, but it's a little bit ironic because Ziad now works for a pharma company. So depending on your view, you may view that as the dark side. But he did a lot of pretty much all the work for that, the groundwork. Okay, so this is a little bit again of a sense of like how we're looking at similar things but in different ways. So on the left here, what we're looking at is a slice of the brain, and we're really looking at like volumes, and we're seeing within the slice that here you get a sense of these are where the tissue boundaries are, and what we really care about, especially with gray matter, is it's not just like a flat layer somewhere, but it wraps around as a cortical sheet that goes all around the white matter. So what we really care about is looking at lots of these things simultaneously and following these around. And then this stretches out of this plane. And so that's why we'd really want a different way of viewing the data. And so with surfaces, we can look at these things and see the whole surface and nothing but the surface all at once. And so this is useful because this we can represent all the information from the gray matter cortical sheet. And we can also play around with the surface a little bit to view it in different ways. So we can make different kinds of projections in the same way when you have a textbook and you want to see a picture of the Earth. You know, it's a bit hard because the Earth is a three-dimensional shell and you want to squash it onto a page. Here we also have to squash things onto the computer screen, but we can do different projections just like Mercator and all these different kinds of map projections to play around with the data so we can see different things simultaneously and how they relate. But everything that Bob talked about, all the statistics and things like that, all that is kind of the same. Instead of thinking about voxel by voxel, these cubes in space, as you can see here, this granularity, what we'll talk about now are these nodes, because what is our surface? We'll take a little more look at it, but it's a mesh. So we have these nodes connected in space. And another important reason beyond just visualization for dealing with surfaces and using surfaces is this distinction between geometry and topology and how they relate to the data and how it's gathered and how it's processed. So geometry is the spatial location of something. It's x, y, z coordinates. So for example, these chairs are kind of arranged in a matrix now, so I could give each of you an ij element location for your seats, and that would be your geometry. And if you got up and moved to a different seat, like if everyone moved forward, but I know nobody wants to, then you'd be changing your geometry, right? Topology is a little bit different. It relates to how things are connected to other things. So basically, if I asked you guys to hold hands with people who are near you, that would be your topology. It doesn't matter so much exactly where you are, that's your geometry. How you connect to things around you, that's your topology. And going back to the first case, if I asked you to move chairs, if you were holding hands and you move chairs with people without breaking your connections, you may be changing your geometry, but your topology would still be the same. So for example, a balloon, if I start with it uninflated, it has a geometry and a topology. As I inflate it, its geometry changes because the location of every point moves further away in space or something, but its topology is the same. The little neighborhoods around each little bit of plastic are the same neighborhoods, so it's topologically the same. And this is an important part. So geometric proximity does not imply topological proximity. And we can see why this might matter in the brain, in that if this is one little bit of cortical sheet and this is another part here, geometrically they're very close. And if I smooth my data or I blur my data, they might get their data merged together, their time series, because they're so close, if I just did it in a volume. However, the information here and here are really quite separate physiologically. They're very far away topologically. Topologically, I have to walk all the way around this yellow part to find the closest distance between them. And so, this is the same different, as you're driving between places, as a crow flies, is different than the roads that you can go on, that kind of idea. But it really matters for processing because the data really does get mushed and smoothed together in different ways. And what you consider your neighbors depends on where you're smushing your data. And so in volume space, these may get mushed together, but they really shouldn't be. So if I project these onto a volume, now if I smooth with my neighbors, the neighbors of B are here and the neighbors of A are here, and nary the twain shall meet, which is more physiologically appropriate. And so it's the same idea. If you live in Morocco and you have a friend in Spain, you can wave at them. If you want to go visit them, you have to go all the way around the Mediterranean. So these are the kind of things that we have to be careful of when we're processing. And we can play around with changing geometry, and these are all topologically the same. So going back to here, all the data is still the same. It's not really being changed. It's just like taking this and reinflating, taking a raisin and rehydrating it or something like that. And this allows us to not lose sight of information that's kind of buried in these sulcal canyons, but we can kind of project it out and see it all at once, throw information on there, see different types of surfaces. We can even look at a spherical projection, and a lot of times this is used for alignment purposes or intermediate steps. So all of these things are really the same data, topologically the same, just played around with geometrically. And when we're looking at things in 3D, we can also play around with the type of information that we can look at. And SUMA provides a lot of methods for looking at different types of information. So Bob mentioned things like connectivity or functional connectivity. So if I have regions in the brain and I want to correlate them with each other and I can measure that. So let's say if I have 8 regions in the brain, I can calculate correlation with all the other, well, with the 7 other parts of it, and I can make it look like a correlation matrix. So this represents regions 1 to 8 and 1 to 8. And so along the diagonal, it's a property with itself, but on these off diagonals, this is a property that relates between, say, region 1 and region 8. And so if this represented functional connectivity, that would be the correlation of those time series. And I could look at that in space to get a sense of, well, for example, I might be interested whether closer parts of the brain have higher correlation or something like that. There's lots of other types of information we can look at, and we'll talk specifically about structural information. And by structural, we mean white matter tracks. And so this is a way of looking at properties on the tracks themselves that may be connecting different regions. Okay, so I'm going to talk a little bit about something different than fMRI, which is called diffusion weighted imaging. And as we take numbers and crunch that, diffusion tensor imaging. And this is what we use to look at local structures, particularly white matter. And I'll talk just very briefly about where the data comes from, and then some of the good sides and bad sides of it, and how we use it for looking at structures, and how we even can try to estimate where structures are in the brain, which is an extremely hard thing to do. Even if you take a histological brain and you freeze it, how do you find out where the structures go? You have to slice it up and then reconnect those little broken bits across these frozen slices that have changed shape even by drying and freezing and all this. So it's a really hard process, and you couldn't do that for living subjects. So we try to do something as best we can computationally. So picking up where Bob left off, a lot of what we care about in fMRI are networks of the brain. So we know that different parts of the brain that are scattered around work together in some sense to do things. And so some studies look at, well, which parts of the brain tend to work together a lot. So these are kind of gray matter or functional networks. And this is from a study of looking at different things. So there's kind of a visual network you can see here. What are some other good? I think this is executive control. There's attention. There's sensory motor, somewhere in here, and sensory motor. And so these are on the functional side. And we can think about gray matter kind of hierarchically looking at different properties. We can look at voxel-wise properties, so what is this spot doing, what is this spot doing? Or we can think of network properties. How are these regions interacting, and are they interacting more tightly or less tightly? And how do those change in different pathologies or across development? But there's both a local kind of voxel by voxel side and a network-wide kind of region by region or sets of regions. And so we can use things like simple correlation. So take the average correlation of this average time series of this region, average one of this region, and correlate them, and do that with lots of regions and make, as I mentioned before, these correlation matrices. And so where they're red, they're more highly correlated. Where they're not, they're less highly correlated. And along the diagonal, the correlation should be 1 because this is just correlating something with itself. And so this is one way that you can quantify kind of a network's worth of properties with this, or average properties with these kind of correlation matrices. With white matter structures, we have different ways of probing it. And we also have the same idea where we want to say, okay, if this little bit of the brain, this kind of voxel, what are some properties of it? So these local properties. And we do that with these kind of inscrutable sets of letters, but we'll talk about what they are a little bit. And then we also have this interest not just in like this isolated bit of white matter here, but especially with white matter, we care about it's providing a connection. So we care about sequences of it all along the way. And so how can we look at kind of network properties or these non-local properties as well? And so this just is a schematic of essentially what we care about, of the important parts of white matter fibers. So they're extended They can go for several centimeters, and they have this myelin sheath and axon structure. And so this is kind of what we're focused on probing with DTI. Okay, so just as a motivating example, let's say someone gave you a functional study and said, okay, these parts of the brain are working together functionally. Great. What can we do to look at their complementary structural properties? Because somehow they must be communicating with each other, and they're not going to all be connected with each other. There may be hubs or other things, but some of them may be. So what we'd be interested in is finding bridges among pairs of them if we can. And again, not everything will be connected to everything. We wouldn't expect it to be, but there may be some. Or if you're going to look for white matter connections, these functional networks is a logical place to start. So kind of complementing these functional studies. And that is the goal or the program that we have for what's called tractography, where we want to try to estimate the most likely locations of where these white matter bridges may be. And once we have those, we want to look at quantitative properties of them. So the set of tools in AFNI for doing this is called FATCAT. So it's Functional and Tractographic Connectivity Analysis Toolbox. I mostly put this here just because it's a fun acronym. And who doesn't like pictures of cats from the internet? Okay, so a lot of this deals with DTI. So what is DTI? Diffusion tensor imaging. It's a subset of MRI. And the diffusion part of it means that we're basing our measurement on looking at the random motion of particles. And basically, anytime you have a fluid, the molecules are sitting in there very small so we don't see it, but they're all jumbling around all the time. And if you, let's say, grabbed 5 of them and painted them one color and then let them go, they're not just going to stay there because they're all bouncing around randomly. So some will go one direction. They could all go in one direction, but kind of statistically, they're equally likely to go anywhere, so they may spread out or something like that. And for us, we're looking with MRI, and a lot of times we focus on hydrogen. That's useful for looking at water because water molecules have 2 hydrogens, so they're kind of a natural marker in there already. The tensor is just a mathematical object. It's a matrix to store this information as we gather it. And this is here quantifying how the particles are spreading out in all directions. And we live in a 3-dimensional world, so it's a 3x3 matrix. This tells us about going the x direction, y direction, and z direction. And the imaging part of it is we want to look at quantitative properties of the brain. And in particular, we're focused on white matter, local properties, and then trying to look for extended structures. So that's just a translation of the methodology. So why use diffusion? What is it useful and how does it work? Well, diffusion is the random motion, so we can think about it as mixing or spreading. And one thing you can do is you can think about taking a tea bag and putting it into like a very large teacup. Now, if you want to make tea, what do you do? Usually, we'll use hot water, but you also stir it, maybe. And what does that do is it jumbles around everything a lot, but that's using not random motion, it's using, you're giving it kind of purposeful motion. However, if you just put the tea bag in and let it sit there for a while, you notice that there would be kind of a growing ball of tea around the tea bag because the water molecules are bouncing around and the tea molecules are essentially just special painted ones. And in an empty cup, everything has equal probability of moving in every direction. So if we look at a lot of these over time, we'd expect that the concentration would just spread out roughly equally. Some go in any given direction. There's no reason for them to prefer any other direction. However, if we change the situation and we put in structures, now it's not so easy for particles to just go in any direction because they run into walls. So maybe as they jostle around here, it's hard to go through the walls, but it's easier to go along the structures. So these are kind of like barriers and impedance, but they're not equal in all directions. They don't impede it equally in all directions. And so if you think about what would the diffusion, what does that mean in terms of the diffusion pattern? Well, it's not equal in all directions. And where it's easier to go, more particles will go more quickly. So we get a non-spherical shape of diffusion. And this is really the major underlying kind of model for what's happening, why DTI is useful, because um, if we can look at the shape of how things are diffusing, we can back infer about structure. And so that's what we're trying to do. So we essentially have these water molecules, hydrogen, in the brain. If we can tell how it's diffusing locally, we can say, I have straws in my brain here, or I don't have any straws in my brain. And if you have straws in your brain, you should seek medical attention. No, we don't have straws. We have white matter, which are, from a physics point of view, straws in this case. So just basically, molecules bounce around and they're affected by local structures. So if I can measure lots of different directions of how something is moving, let's say in this direction it moves a little bit, in this direction it moves a lot, and here intermediate. Well, if I combine all those measures, and if I just have these brown arrows, I can make kind of a model for what's happening. I can say, well, it's generally easier to move along here than along here, and I would infer back something about my structure. This is what we do in diffusion tensor imaging. So we don't have this. I'm showing the green background here, but we don't have it. That's what we're trying to estimate about. And if you notice, in this case, actually, there's lots of structure. It's not just like a set of straws all uniformly oriented. And it is true that in any given location we're looking, the structure will probably be complicated. And we could try to say, well, can I get a sense of this finer, more complicated structure? And there are ways to try to do that. I'm not going to talk about them here. Everything I talk about related to DTI relates to these other diffusion-related methods. It's just slightly more complicated. So this is everyone's favorite thing to look at mid-afternoon after lunch, after a couple hours of lecture, mathematics. So eigenvectors and eigenvalues, and this is all very nice. I just put this up here to say that there are real quantitative mathematical properties, but the nice thing actually, especially from the point of view of giving a talk, is that having a 3x3 matrix with these properties is actually the same mathematical structure as ellipsoids. And so these kind of algebraic quantities correspond exactly to these geometric things of a sphere or pushing out a sphere into these spheroids like a rugby ball and things like that. So when I talk about these things, or when we picture them, this is actually mathematically equivalent. So we can just kind of deal with this nicely geometrically and know that we have mathematics that we can use and quantify things with. So this would be isotropic diffusion. So it's equally probabilistic to go in any different direction. And this is anisotropic. And then we can quantify it based on these things. So every bit of these fun mathematical terms corresponds to something that I prefer, because I like pictures and geometry. So our tensor is really just the ellipsoid surface. The eigenvectors tell us how we're oriented in space. So that's what these orange arrows represent. So this is a two-dimensional object. It has two axes we could rotate around. And in 3 dimensions, it would have a third one, in this case, like sticking out of the computer. And the eigenvalues tell me how pointy the ellipsoid is in a given direction of the major axes. Okay, so a special case is a circle, or in 3 dimensions, a sphere, and these dirigible type things are. And the only other thing that really matters is, we have this 3x3 matrix. This is also symmetric. And the only reason that's really important is when we're acquiring data, we need at least 6 measurements to be able to do this. And you can think about that, whereas if I gave you like a cardboard box and I put a sports ball inside of it, and I said, I want you to guess what that is by poking it. You can't just reach in and poke it once and know what it is. Because if you just poke it once, you don't know whether it's spherical, whether it's a square, whatever it is. You have to poke it lots of times from lots of different directions. And the same thing is what we're doing here. Essentially, we're trying to say, how much is the diffusion in a given direction. We have to look in lots of different directions, at a minimum 6, because we have 6 independent quantities. In general, we usually make a lot more measurements because it's a very noisy environment. And if you appreciate anything from Bob's talk and mine, fMRI and DTI a lot of MRI in general is very, very noisy, and so a lot of what we have to do is deal with distortions, noise, and trying to clean things up. That's why we're all employed. Okay, so just as a cartoon example, if I showed you these things, so one is gray matter, which is just these kind of structures, and white matter. So in your head, think about the relative properties of an ellipsoid that you might have with these. And so essentially, which one's going to be more spherical? This is open for discussion. You can say left or right. Which one will be more spherical, do you think? If you're wrong, I will throw you out. So that's a good, you get to leave early, but. Hello? Any takers for the right side? Yes, probably yes. So yes. So I didn't mention what these things are, but this one here, basically, if you're trying to move through here, it's equally a jumbled mess in any direction. So that probabilistically that translates to kind of roughly isotropic diffusion or a spherical shape. And here, it's really easy to go here and hard here, so that's why you'd have it a pointier. And we quantify these things. So what this FA stands for fractional anisotropy, which is basically just tells you how relatively, no, how differentially easy it is to move in a different direction. So here FA is 0 because it's equally easy. As it gets easier to go in one direction relative to another, your FA increases. All right, how about in this case? So now I just have white matter and white matter. So which one will be pointier? Which one would have a pointier diffusion shape if I measured it? Left or right? To the right? Okay, and why is that? They're both white matter, so why should one be different than another? Because what's the important property here? It's the kind of differentialness of it. So jumbled white matter or nicely organized white matter, it's different. They're both white matter, but it's the jumbliness. So yeah, I would think that kind of this one, it is hard to move, or roughly hard to move equally hard to move in any given direction, whereas here it's not. So the type of tissue may not really matter. It's kind of the property of ease of motion. Okay, and we also look at things like we use FA to kind of probe maybe white matter bundle density. So maybe they're all organized the same, but if they're so far apart, it's easy to move, then it may not matter. Or we could think about developing brains, myelinated kind of fatty tubes where it's harder to get through versus kind of weak barriers. So these may be the kind of differences we would hope to probe with FA. And so in general, we use this kind of pointiness, and these other properties relate to just basically the size or how relatively easy it is to move in just a single direction. And if you notice too, we kind of get for free in any case, not just is there structure, but if we see structure, the shape of it always tells us how that structure is running, right? This ellipsoid isn't drawn like this because it's going to tell me just A, there is structure, and B, how is it oriented in space. And that's what the eigenvectors tell me. Okay, so these are the kind of basic properties that we tend to look at and try to quantify with these. Does that make sense for how I'm relating these things? Okay. Now, in reality, so those are kind of cartoon pictures. Reality is much more complicated. So, for example, just as we showed, just because you have kind of a spherical shape of diffusion, you may not know whether you're in white matter or gray matter. Remember this example, whereas if you just see spherical diffusion, do you know that it's this case or this case that's physiologically causing it? You don't. So we have lost information. We have these relative measures, but we don't know. All of these may have similar root or different root underlying causes. A lot of times, actually, you can get some pretty significant changes in myelination that may have small effects on FA. I haven't drawn these to scale, but the voxels that we're looking at are maybe 2 millimeters by 2 millimeters by 2 millimeters, Relative to that, axonal diameters are several orders of magnitude smaller. So these are like little tiny strings running through a big cardboard box or something, and there could be lots and lots of them. So there's lots of structure going on. It can be very complicated. And also there's more to diffusion than just structure. So all I focused on is where, how the straws are or something like that. But diffusion, there's a reason you don't just put a tea bag into a jar of honey and try to make tea, right? Would that be Turkish tea? Is that sweet enough? I don't know. No? Okay. Just for the record, Okan's laughing, so that's preserved now in history. But different types. So as you change properties of the, because chemical composition and things like that really matter. So you may have degeneracies of interpretations as well. And then we're always fighting against noise and distortions and things like that. And those can really change how we interpret our measures. We need to account for that. And what does noise do? If you want to think about geometrically, well, if I've estimated this nice ellipsoid shape that represents diffusion, so in this case, let's say the gray fit is the unnoisy, so I would assume that my structure is running here. What does noise do? It makes my fit wrong. And it can be wrong in a couple different ways. It could squash my ellipsoid, so there may be a lot of structure and it gets squashed down to a roughly homogeneous shape, or vice versa. And it would also rotate it. So instead of, let's say this is the reality and my noisy fit. So now I'm starting to think, well, white matter might be running this way when actually it's running that way. So these are the kind of things that can happen to our program of looking at structure. And speaking of which, so this is just, again, motivating why we care about tractography. So we know that the brain is wired, and it's really hard to get an idea of structure, even if we have a post-mortem brain. It starts changing structure very quickly. And it would be very hard to relate to functional connectivity because the person's dead. So what we want to try to do is reconstruct as much as possible structural information that's non-local using quantitative measures, computational things. And basically the way it works is, well, at every location in the brain, at voxel by voxel, we have these measures of these ellipsoids. And where they're pointy means we think there's structure there, so that we can record where they're oriented in space and store them in this grid. And then if you look at these, you might think, well, I have a lot of pointy ellipsoids that look like they're running into each other. And we know, white matter should be, in lots of cases, longer than a voxel. So it's much skinnier than a voxel, but also a lot of it is much longer than it. So we might try to connect these and say, well, this is where we would guess the structure is running. So we take our local measures, we come up with some kind of rule for gluing them together. And from that, we look for spatial extent of white matter. Here, for example, in the corpus callosum. And this is something we can do without killing the patient. So this is an example of looking at what's called whole brain tractography. And so this is kind of a coronal view looking at you, and this is a view where it'd be an axial view. And so the color coding is by local orientation of structure. So red is left, right, and this is your corpus. This is the corpus callosum. Green is anterior, posterior, so you can see a bit of cingulate bundles here. And blue is inferior, superior, so you can see here the cortical spinal tracts starting to run up from the base of the brain. And this is actually my brain, so there you go. You learned more about me today than you probably thought you would. Okay, but well, we can get these kind of pictures and everything, and I always put this in you're all here kind of doing science and learning about science. This is really an important thing. So does anyone know what GIGO stands for? Bonus points if you do. The first word is garbage. Yeah. Oh, see, okay. Garbage in, garbage out. And so Charles Babbage is the person who kind of made the first computational device in some sense, or one of the very early ones. He made it out of wood. And so so he's relaying this, he's a mathematician. He said, someone asked him, if you put into the machine wrong figures, will the right answers come out? And he just couldn't understand how people could possibly think this. But there was this kind of, people didn't really understand what computers were. And I think, this is in the early 18th century, early mid 18th century, 1800s. And I really think that probably this problem has only gotten worse today because people just think, well, I ran it and my program didn't crash, so it must be good. And so this is just me on my soapbox. And part of the AFNI stuff as well, why we talk a lot about visualizing data and things like this. It really matters that you look at your data and you think about ahead of time what you're going to get, because if bad stuff goes in, it's too complicated to compare every set of numbers along the way. So it's really important to be careful of how you process your data. So from a DTI point of view, if anyone's ever doing this, this is a tool that we use. One of the esteemed authors of the tools is amongst us. Later on in the summer, I think Carlo Pierpaoli will talk, and Joel Sarles will talk about DTI, and they both know a lot about acquiring and processing data and things to watch out for. So that will also be educational. And just the kind of thing, it can really affect the kind of measures you get if you don't pre-process your data. And I think something equivalent will apply in anything you're doing here this summer. That if you have distortions in your data when you try to estimate tracts, so this is what you would get versus representing your cortical spinal tract, this is really much more what you should get. I call this the sick grasshopper because that's what it looks like. And to me, this looks like kind of a graceful ballerina. So you want to have your data processed well, so you have more of this. Okay, and so talking about this program and some of these cartoon pictures, we might think that this is a pretty easy thing to do. It's actually hard, and there's a lot of beast-likeness to it. So as I mentioned, axon diameters are really tiny, and also structure is really complicated, right? These are not the nice clean straws separated out. And so if you really want to see where these structures go, you really have to have people volunteering their time on a computer like Sebastian Sung kind of set up. He's a computer scientist. So people, as a game, they get these slices of data and they kind of color which ones look like they're running into different voxels and things like that. And so it's really very intensive work. And even if you have something like that, from what we're looking at, if you have complicated structures, you don't know what happens inside your voxel. So we may have structures going in and out, but we don't know whether they cross or what's called kissing. And so there's always these kind of inherent unknowns with what's happening within a given voxel. And some other work that's been done is kind of looking at with human tracing data, showing that basically there's a trade-off in this between, it's called specificity and sensitivity. So getting lots of false, you want to try to get false positives minimized or false negatives minimized, right? You don't want to miss out on tracks, but you don't want to include false stuff that would lead you astray. And this is a really hard thing to do. And this is still a problem with the field and with methods and that people are working on. So there's a lot of known problems with it. That being said, a lot of serious people who know biology and care about biology and doing clinical planning, things like that for surgeries, do find tractography useful in some sense, and kind of that it does consistently reproduce a lot of major known pathways. And this can be useful because basically we don't have a good alternative for parcellating the white matter skeleton. So if I want to compare your brain and your brain and your brain, and I want to take a look at small regions of, you want to take a look at like small regions and compare those, how else are you can do it besides this? There really isn't a good alternative, and there are a lot of major pathways that are reproducible. And from a surgical point of view, people actually do use this for helping to give more information for planting electrodes in the brain. So the alternative is just to get a nice structural image and say, well, I think this bumpy structure ends here. Let me jab this metal fork into your brain here and hope for the best. And so I don't know if anyone is working in a deep brain stimulation project, but they do just stick a metal thing into your brain, and it has usually 4 different electrodes that you can vary the voltage on. And they stick in a lot at a time because they don't want to keep moving it around. So they kind of put it in where they think, and they turn things on and off and crank up the voltages and down. And what people have started doing for a couple different applications is using tractography to help locate really where you are in the brain based on where pathways seem to be going. And that means that they get a little more closer to where they want to be sooner in the process of trying to guess where they are in your brain. And so this has been done here at NIH for applications to treating Parkinson's disease. So electrical stimulation has been found to help that, and also for treatment-resistant depression. This is from a group in Emory University. And basically they use tracking to find a set of paths, and then they aim for this region through the intersection. So this tracking gives a lot more information than just the structural anatomical by itself. Okay, so at the end of the day, what do we use this information before? Well, we know that gray matter regions somehow are connected by white matter skeleton. Right? That is what white matter does, it connects things. And we want to try to use tracking to estimate where are the most likely locations, and in particular, functionally related gray matter regions seems like a useful place to start because at least some of those should be connected, right? That's why they're functionally related. Once we have those, then we want to kind of quantify properties of that white matter, looking for maybe lesions somewhere or something like that. And basically that is the program of tractography, to try to parcellate the white matter skeleton from the subject's own data, because pathways can kind of go in slightly different ways, so using atlases may be tricky. And now and forevermore, please don't think of these as like literal connections, but they're really kind of probabilistic things of like, I think that the structures are kind of mostly going like this. And so if I see 10 of them in one brain and 20 in another brain, I'm not thinking that this person's brain is a lot more tightly wired than person A, but it's just from a probabilistic sense within the person's brain. Okay, and then once we have these things, so we can look for regions, going back to what we said before, we have gray matter regions and we're looking for these bridges. So we might perform functional study and get these regions, and so now these are just kind of targets for our tracking, and we want to say, well, where are tracks connecting any of these regions that I think are there? And this is something where you really need three-dimensional visualization, because we're looking for these linear structures, and if you just look at them on a plane like this, you might see a little bit, but you can see that these things kind of would go in and out of planes, and they may have very complicated geometry. So we may care about tracks that connect volumes. It's kind of AND logic. They hit at least 2 regions. Or you may be interested in tracks that go through at least 1 region. And there are different ways you would want to deal with visualizing the data or trying to understand, what is your question about how these functional networks work. And an even better way of going, so here we kind of do this algorithm to connect the regions, and that's fine. We can do a little bit more work and do what's called probabilistic tractography, where we perform lots and lots of iterations of this, and we perturb the data every time, and then we keep a record of locations where tracks keep going even though I'm perturbing the data. So our data is noisy, it's distorted, we know we have noise in there. We try to take into account for that by doing what are called Monte Carlo simulations, which just mean I do lots of random perturbations over and over and over again and try to get a sense of, I believe these a lot more, hopefully my noise isn't affecting me as much. It's a lot more robust, and then potentially snarky slides of showing how it's better than other software, but you guys know that already, so that's fine. Okay. And just to mention at the end of the day, what do we get quantitatively out of this? Well, from fMRI studies, I might correlate time series among like 8 pairs of regions or something. And that's my functional information. Well, if I take those 8 regions and look for any tracks among them, then I can take a look at structural properties along that. And so I potentially also have an 8x8 matrix of information as well. So I can think about storing all my quantities of, instead of looking at functional connectivity between regions, now I'm looking at structural connections and those properties. And then now I have another matrix to play around with quantitatively. Okay, so that is the less fun stuff. I'll show you a little bit about visualization. Okay, so this is starting to look at a bit of summa on the left and AFNI on the right. And as you saw before, Bob showed briefly, this is an axial slice of the brain, and we can scroll around through it. You can see a little bit down here how I'm moving through it. So this is one representation that's nice. This is a nice three-dimensional object, and it has benefits that you can look all around it. And if you want to, you can see the sulcal and gyral patterns and things like that. And if you want to make a nice screensaver, you can also do things like that. But this again is really useful. You can see these things. One problem might be that it's a little bit hard to see inside at the medial regions, but one way around that is we can open it up and take a look at what's inside and close it back up. Maybe. Oh, it's hard. Okay. Now, what are we looking at here? If I zoom in here, we see eventually that we're looking at this kind of voxel structure, and it gets granular. What are we looking at here? This is a surface, and it has a mesh. And so what does that mean? It looks just like a nice surface, but it's really not. This is what we mean by a mesh. It's a bunch of nodes connected by edges. And this is what we mean by topology. And so if I zoom in, this is a node, that's a node, that's a node, and their topology is how they're connected. And if I do this, you can see, can you see, does it look dusty? Those are the nodes. You can see, it's like zooming through space. And if I zoom out, you get a little more sense of the structure there, right? Those are all the nodes, and it's gone. Okay, but it's back. So these are the different representations we have, so we throw data up like that. And if you remember our discussion earlier of topology and things like that, this is one representation, has a geometry and a topology. I can change how it's viewed. This is a peel surface here. This is a geometrically different but topologically similar view to what we had before. So I still have my mesh there. There. It's still a mesh, or a mess, depending on point of view. And it's still the same mesh, just smushed around. And we can view it. This always reminds me of like, big game hunters or something like this, and then they kill a zebra and squish it on their hearth. I'm a vegetarian, it's okay, I can say that. And this is another view of each hemisphere as a sphere. Did I offend you with the zebra comment? You're going to tell Francis Collins, I can tell. And something we can do, Bob showed a little bit here of looking at data. Let's look at just a set here. So this is how we might view data in AFNI, and I'm just going to change the range a little bit. Let's see here. So there's numbers at every location, and they have meaning. Well, don't have to get into it. That's fine. But we can look a little bit more that the nice thing about AFNI and summa is that they're programmed together. And what that means is they can send information back and forth. So I can represent information on one and send it to the other one. And so if you see here, these are the outlines. So this is the surface, and this is where it would appear in the volume space. So these things both occupy the same space, but they're different representations. And so this is what I'm projecting the surface into here, and you can, let's say I can zoom in a little bit here. So you can see this is where it is. And now wherever this intersection is happening, that color is being brought here, and that color represents a number that's important somehow in the data set. And so I can visualize it here. And it happens interactively, so as I change stuff about it, let's say I can change the thresholds aren't so meaningful now or something. But as I threshold my information here, the same thing, the threshold applies here. And so this can be really useful because now I can, for example, with what Bob was showing with statistical information, I can look at it in a slice and okay, but it's a little hard for me to see, is this the whole visual cortex and I'd have to go through lots of different slides. Well, I can just project all of that and the clusters and the this and the that here, and I can play around with how it's viewed, so how it's most meaningful to me. So now I can see, okay, it's really going through these sulci and gyri, or etc.
How is switching between different views?
The this aspect,
Yeah.
the period or full stop key. Period, full stop. Okay, so that gives you a sense of how information, kind of volumetric information can be thrown back and forth. Okay, now what I had mentioned before was what's called tractography. So this is not my brain, but this is what we just looked at a little before, this kind of whole brain tracking. And again, the color is by local orientation. So the corpus callosum is always kind of red because it's these left-right connections here. And now I can view also kind of usefully this with embedded embedded slices to help locate me in the brain, which may be useful. And I can also do things like this. This is kind of every possible connection in the brain, well, every possible tract that was estimated in the brain. I can do something what's called making a mask, and now it's a little hard to see. There, can you see that there's this thing here, and if I move it around, it's a ball. So what I'm doing is I'm selecting a subset of tracks that just go through this region. So I could maybe investigate something I might be interested in, some region, or see where tracks are. And I can look at this in space, and I can see, okay, this intersects a cingulate bundle, etc. And there's lots of, I can add more of these things. I can change the shape and its properties and things like that. And I can even look at it against a background. Maybe this is my favorite part of this. I can look at it against a background of other tracks, so I know where it is with relation to everything else, the kind of dimmer ones. So maybe for something surgical planning or just investigating your data in various ways, this may be useful. But again, this really depends on having a three-dimensional representation, so I can put these lines and things in that are embedded. And this is a view representation. I can also view simultaneously this kind of gold popcorn are the functional regions that we were looking at before, and I can see where the tracks are that are connecting them, again, in three-dimensional space. So something like this might be useful for, let's say, surgical planning. If you didn't want to disrupt a particular network or something, you can see where the gray matter regions are, where we'd estimate kind of white matter might be. And so if I wanted to, okay, I want to enter something through here, not through here where I'm going to run into a particular track, possibly. So these kind of 3D views of combining information are useful. And this is a way now I can combine my structural information of my surface as well as this kind of slice-wise view with the tracks. And I may be interested in opening up the brain and seeing where the tracks are. And if I'm interested again in a subset of things, then I can bring back my magical region, and I can move it around and investigate things. I can click on the tracks to move it around, and I can also click on the surface, and it remembers where it would be when it's closed. So this is a visual representation. So I can say, okay, I'm clicking on this part of the surface. If it were closed, it would be here, and that's where it would intersect these tracks. So you can combine the information in lots of useful ways, right? So if I close the brain now, you see these things match. as I open it, it has kind of an avatar here for where I was clicking. That's where it belongs. Or there are ways I can play around with opacity if I want to see the outside and inside simultaneously. Lots of different ways to view the data. So we always talk about this kind of correlation of time series and things like that. And so I'm going to set up something very, very quickly. So we can investigate a lot of these things interactively. And if I can just get my panel here. So I'm setting up something which is called Instacore. So we can actually look at the correlation of the time series in kind of real time. And this is something that Bob set up. So what we might be interested in is I have my data, and I say I have this region here, and I want to see what is it functionally connected to elsewhere. Now let's see, there's a little bit of lag at the moment. It was catching up where I was clicking. Okay, and let me just reduce the threshold. Okay, so right now it's thresholding at 0.5, which is a little higher than I might want. But this shows me in kind of real time as I click around through a data set what other parts of the brain are highly connected functionally to this. Now, we were looking just at before something a little bit similar here, where we say I have a region and I might be interested in where there's, come on, where there are structural connections through a region. So let me put a mask here. And I have my regions of the brain like this. And we showed before that what I can do is I can click around and look for where there are tracks related to what I have. A bit smaller. So this shows me the kind of structural connections that are going through here. In my functional data, if I click around here, I'm looking at where parts are functionally related. And if I want to, I can actually combine these so that, remember we said I could make these talk to each other. So what I can do now is wherever there is correlation here, I can view it in my data set here. So this is part of the visual cortex. And what I can do is I can update both. So I can click on a region and look at both how it's functionally and structurally connected simultaneously. So as I update my location here and look at functional regions, I can say, well, there's high correlation between this part here and here, and what does that look like in the, oops, what does that look like in my three-dimensional brain? And I can click around here and update it from this side as well. So now when I say, okay, this is where I am here, I move here, and I also have it structurally, functionally connected. So I can view anatomical, structural, and functional connectivity all at once. Are there any questions on that? Okay, so that's been a brief tutorial of, set the threshold low. Maybe this is a little easier. It just shows a bit more. Okay, so between Bob and my talk, you're all masters of brain imaging and visualization now, so congratulations.